Hi everyone, welcome to video 8, section 3.4, concavity and the second derivative test. The first thing we're going to look at is concavity, so we need to define what that is. So let f be the differentiable, or let f be differentiable on the open interval I. The graph of f is concave up, okay, on I, the interval, if f prime is increasing, and it is concave down on that interval if f prime is decreasing. So we will use concave up, we will let that stand CU, and concave down we will say CD, just so you are aware of the notation there. Okay, so if we take a look in this first graph here, the graph of f lies above its tangent line. F prime is increasing here, okay? And therefore we can say we're concave up. Here, we're concave downward. In this second example, f prime is decreasing. All right, so we're concave down over here. F lies below the tangent lines. So then how do we test for concavity? Well, the way we test for concavity is if f is the function whose second derivative exists. So now we're looking at f double prime, the second derivative. So if the second derivative exists, okay, if f double prime is positive for all x on that interval, then f is concave upward on that interval. So f double prime is positive, we're concave up, all right? So f double prime positive, concave up. If f double prime is negative on the interval, we are concave downward. Okay, and we'll go through an example of how we figure this out. Okay, so now we need to talk about points of inflection. So the definition of a point of inflection: let f be a function that is continuous on an open interval and c be a point on the interval. If the graph of f has a tangent line at this point, c, f of c, then this is a point of inflection of the graph of f if the concavity of f changes from upward to downward or vice versa. Okay? So point of inflection is if the concavity changes from upward to downward or downward to upward at that point. So how do we find points of inflection? Okay? So again, if c comma f of c is a point of inflection, then either f double prime of c equals 0 or f double prime does not exist at x equals c. So it's very similar to finding those critical numbers with f prime, but this is dealing with f double prime and points of inflection. So if we take a look at these three scenarios here for points of inflection, okay, we can see here we are concave down, but then we start to be we're concave up here, and then we switch to concave down. So we have a point of inflection right here, okay? If we take a look here, we're concave down, and then all of a sudden we switch to concave up, another point of inflection, okay? This would be a case where f double prime doesn't exist, but we still have a continuous function here, and concave down, all of a sudden we switch to concave up, all of a sudden we switch to concave down. So we do still have a point of inflection. Now we're going to talk about the second derivative test. Okay, so what is the second derivative test? Well, just like the first derivative test, the second derivative test is used to find relative extrema. It has nothing to do with concavity, okay? So we're going to let f be a function such that f prime of c equals 0, meaning we've got a critical number, okay? And the second derivative of f exists on the open interval, okay? So c is a critical number. So if f double prime, second derivative, of c is greater than 0, then we have a relative minimum at c comma f of c. If f double prime of c is less than 0, then we have a relative maximum at c comma f of c. All right, so if f double prime of c equals 0, second derivative test fails. Okay, so then we would have to go to the first derivative test. So we can't necessarily say that it's a relative minimum or a relative maximum or neither. You have to go back to the first derivative test. So something I want you to note about the second derivative test. Okay, it has nothing to do with concavity. It's just another way to find extrema if f double prime is easy to find. If f double prime isn't easy to find, don't use the second derivative test. Okay, and again, it has nothing to do with concavity. The concavity is our concavity test, and I will go through an example very shortly. Okay, let's go through this first example here. We are given the function f of x equals x to the fourth minus 4x cubed. Our goal is to find any and all points of inflection. We're going to talk about that concavity, and we're going to talk about the relative extrema by using the second derivative test if we can. Okay, so the first thing we need to do is, if I'm talking about points of inflection or concavity or relative extrema, we need our derivatives, right? So the first thing I do is I find what f prime is. So f prime is 4x cubed minus 12x squared. We need to find our critical numbers, so we set it equal to 0, and we get our two critical numbers here. We use these critical numbers with the first derivative test and the second derivative test. Okay, so we kind of put these off to the side. But now to talk about concavity, we need our second derivative test as well. Or sorry, our second derivative, not the second derivative test. So f double prime is going to be 12x squared minus 24x. To find our possible points of inflection, we set this equal to 0. So we factor, and we get two possible points of inflection. So I call those PPOI, possible points of inflection. I have to use the concavity test to determine if they actually are points of inflection. Okay? All right. So now we go to finding our points of inflection by testing concavity with our possible points of inflection. So this is going to look like our first derivative test that we've been doing the last couple of days. So what I do is I draw my number line, okay? I put my possible points of inflection on here, and we have our three different regions. So now I want to know what is the value of f double prime, because if f double prime is positive, we are concave up, and if it's negative, we're concave down. So remember, points of inflection occur when f double prime changes sign from concave up to concave down or vice versa. So what we should notice is, again, testing in f double prime, we're going to get a positive value for less than 0. So that means we're going to be concave up on this interval. From 0 to 2, plugging in a point into f double prime, we're going to get a negative answer. So that means on that interval, we are concave down. And then if I test a point in this region over here into f double prime, we will get a positive value. So that means we are concave up. So since we go from concave up to concave down at x equals 0, we have a point of inflection at 0, and when I plug that into f, I get 0 as well. So the point is 0, 0. And then if I have another point, since I go from concave down to concave up at x equals 2, I know we have another point of inflection, and when I plug 2 into f, I get negative 16. So we're using the concavity test to find our points of inflection and determining that from f double prime value. Okay, now we're ready to determine some relative extrema. Okay, so since our second derivative was pretty easily found, we can use the second derivative test with our critical numbers, okay, from the first derivative. So remember, our critical numbers were x equals 0 and x equals 3. So we can plug in these values into our second derivative test. So when I plug 0 into f double prime, we get 0. This is an issue because remember, this fails the second derivative test. So in order to determine any relative extrema, we have to go back to the first derivative test, just at x equals 0. So I go through my first derivative test, I plug 0 in, my critical number, I take a look at the f prime value. It's negative to the left of 0 and to the right of 0. That means f is decreasing and decreasing the whole time. So since we're decreasing and f prime has no sign change by the first derivative test, there is no relative extrema at x equals 0, since there's no sign change of f prime. Okay, so now let's check x equals 3. So again, we're plugging this critical number into the second derivative. Sorry about that, they're testing some of the bells. Anyways, when you plug 3, the critical number, into f double prime, we get 36, which is greater than 0. So that works. So we can say by the second derivative test, we have a relative minimum at x equals 3. And if we wanted to be more specific, we know that the point occurs at 3, negative 27. Okay, now let's put it all together and let's try graphing these. Okay, so a side note, really quickly, what we wanted to do for f is we can set this equal to 0 and find any zeros for f. So if I take out an x cubed, we're left with x minus 4, and we get two zeros, x equals 0 and x equals 4. So if I'm going to go ahead and plot those, now my f function is this black function, that black graph there. So I'm going to plot my zeros, 0 and 4. We know we have a relative minimum at 3, negative 27. We know we have points of inflection at 0, 0, and at 2, negative 16. Okay? So we're going to use that fact. We also know from that first derivative test that we tested with our critical point of x equals 0 that f is going to be decreasing from 0 to 2. Okay? We also know that we're going to be concave up from negative infinity to 0, concave down from 0 to 2, and concave up from 2 to infinity. So that's going to help me graph. Okay, so I know starting far left, I'm going to be concave down. Sorry, concave up. I keep mixing those up. We are concave up. Once I hit 0, my graph changes to concave down. Once I hit x equals 2, I'm back to concave up, and I will be concave up all the way through. So there is our graph of f. So now we need to graph f prime, okay? So one thing we should know is, well, we do know that we have some critical numbers or zeros at x equals 0 and x equals 3, okay? By our first derivative test, we know that f prime is negative from 0 all the way to 2. And once we get to 0 to 3, once we get to 3, we're going to be positive. So we know we're negative, negative, negative. We have that 0. We go back. We're still negative, negative, negative. And now f prime is positive. So it's going to be our blue function here. And now we zoom in and we find our f double prime. So we can take a look at this graph, or we know that it's this equation right here. We have ourselves a quadratic, so we should have a parabola that opens up, okay? We know f double prime is positive from negative infinity to 0. We know f double prime is negative from 0 to 2. And we know f double prime is positive from 2 on. We had to do a little bit of work to find that the vertex is at 1, negative 12. We have our two zeros, so we can go ahead and graph our parabola like so. If you have questions, let me know. We'll go through it in class. This last example, I want you to look at it. I want you to sketch the graph of the function having the following characteristics. So I want you to take a look at those characteristics. I want you to determine if you can identify any critical numbers. I want you to determine if you can identify the concavity and give the graph a shot. So pause the video, try it, and then check back. Okay, so here's my thought process on something like this. I know f of 0 equals f of 2, which is 0. So I know I've got two zeros in my graph. So I can plot those. This is saying f prime is less than 0 if x is less than 1. It then says f prime is greater than 0 if x is greater than 1. And it says f prime of 1 equals 0. So this right here is showing me f prime is going from negative to positive at x equals 1. So x equals 1 is a critical number, and it turns out it's a relative minimum because we're going from negative to positive. Okay? F double prime is greater than 0 tells me we are concave up. Okay? So I can go ahead and draw my critical number in, my vertical dashed line, just to kind of give me some guidance. I know to the left of that, f prime is negative, which means f is decreasing. To the right of that, f prime is positive, which means f is increasing. Now this point right here, that's just general. You could have put it anywhere, but you should have a relative minimum somewhere along this line here. And we know we are going to be decreasing up into that point and then increasing after x equals 1. So hopefully you got it. If you have any questions, make sure you ask those in class.